Hello students, my name is Shashank Shekhar and today is the 7th day of the chapter Haloalkanes and Haloarenes. So yesterday we have seen the stereochemical aspect of this SN1 and SN2 reaction, and we are left with this SNI. So this is one more type of substitution which is named as SNI, and this SNI results in the retention of your configuration. So if you look at the syllabus, so here are we right now. So we are in the optical rotation mechanism of the substitution reaction. So we are done with this. So we are now looking at some of the reactions. So basically, so today we will mainly focus on this elimination reaction and reaction with metals. Okay, so let us start our lecture. So to begin with the lecture, we will start with this SNI reaction. First of all, we will see the left out substitution reaction. Then we will see what is elimination reaction once again in more detail, and the types of elimination reaction, that is E1, its example, then E2 and its example, and then we will see what is the difference between this SATHEE-MED and Hofmann. So yesterday I mentioned that two products are possible in case of unsymmetrical alkene. So how we will decide that which alkene will form? We will see that which type of products, or you can say substrate, gives your SATHEE-MED and which type of substrate gives your Hofmann. After that, we'll see what is this E1CV reaction. So this is also a kind of elimination reaction, and it is very common, but you would have not noticed it. Okay, just I will give a name to it. Moving to this second and the most important thing after all of these reactions is that when do we do this substitution reaction and when do we do this elimination reaction. So this thing is very important. So we'll look at this. At last, we'll see what is the process for the reaction with metals, or how does haloalkane react with metals. So let us start with SNI reaction. So here is the example of SNI reaction. Okay, so the aliphatic nucleophilic substitution reaction leading to retention of configuration. Okay, so this leads to retention of configuration. So I have told it earlier also. It is a kind of internal nucleophilic substitution. What it is a kind of internal nucleophilic substitution. How is it so? So we'll look at it. Now this is an example of your SNI reaction. So I have mentioned it twice in the haloalkane. So I am again mentioning the mechanism once more, which is more clear here. So this substitution, which is you can see here, is an example of SNI mechanism. And suppose R was the configuration of the reactant, then it will remain same. Okay, I will not say remain same. I would say that the position, the spatial arrangement of all these three substituents, both in the reactant and products, will remain same with respect to the leaving and coming group. I would say this would be better to say. Okay, so configuration can change. Suppose something is substituted that has a lower priority, then in that case, maybe we cannot get this retention, or you can say we cannot get this retention, right? Okay. So to begin with this mechanism, first of all, the OH that is present, this O attacks the SOCl2 and this Cl leaves, right? This Cl leaves. So in the first attack, suppose this substrate changes its configuration. So is there any change of configuration? So you can see that there is no change of configuration here. Okay, because this O is attacking on this thing. If this say our reagent has any configuration, then it would have been changed, but we cannot see any effect on this this configuration of the substrate. Okay, but at the second part, what happens now? This Cl attacks from the same part where the O leaves. So there is no such back attack or no formation of carbocation. Therefore, you can see that where the O is leaving, or the OH part is leaving, there only the Cl part is coming. Okay, this Cl part is coming on that part only. Due to this reason, so if I say that this is having R configuration, then this product will also have R configuration if OH and Cl priority does not changes, or you can say the spatial arrangement of all these three does not changes with respect to this, both in case of reactant and product. So this is SNI. This is the third type of substitution reaction, and this leads to retention of your initial reactant or in retention of the configuration of the initial reactant. Yesterday, I have mentioned this elimination reaction. So basically what happens here is that the beta hydrogen is heated with alcoholic solution of, so I'm talking about this haloalkane. So we are taking this case only because we are in this chapter. So what we will do, we will take a halogen which has a beta hydrogen. So I will tell you later what is this beta hydrogen, how do we specify it, but just for now imagine it that this is our beta hydrogen. Now we heat that beta hydrogen containing halogen, this is a halogen, with alcoholic solution, okay, of potassium hydroxide. So suppose in the exam it is given like this, ethanol. Then you will say that okay, this is your alcoholic solution of potassium hydroxide and it will give you elimination reaction. So do not get confused. You will not be given directly that you have to take the reagent as alcoholic H. Instead it can be written like this in the form of one alcohol and your potassium hydroxide. Okay, this is clear. Okay, now there is a elimination of this hydrogen. So you can see that this hydrogen has been removed from here and an alkene has been formed between this carbon and this shared pair of your say bond pair has been now shared between carbon and hydrogen, which was initially between carbon and now this bond pair between carbon and hydrogen is now shared between carbon and carbon, and we got our base with hydrogen abstracted and the leaving group X. Okay, so this is the thing. Now what is this alpha and beta carbon? Okay, now what is this location of this alpha and beta carbon? So this carbon which contains the halogen that is to be removed, that carbon is called as alpha carbon, and any carbon that is just next to it, either suppose there is a C here or a C here, then all of these three carbons would be called as beta carbon. So is this clear to you? So I am saying here that suppose you have an halogen and the carbon containing halogen is this one, then the every carbon that is directly connected to this carbon will be termed as beta carbon, and the hydrogen connected to that beta carbon is termed as beta hydrogen. Okay, so the carbon on which the halogen atom is present directly attached is called alpha carbon, and the carbon atom adjacent to this carbon atom is called beta carbon. So adjacent carbon means next carbon or consecutive carbon is called as beta carbon. Then we have gamma, alpha, beta, gamma, delta. So that is the sequence. We do not have to worry about it. But for now, just remember the thing that if your halogen is connected to some carbon, then and the carbon is to be removed, the halogen is to be removed is that only, then that carbon will be your alpha carbon, and the next adjacent carbon or the consecutive carbon, if suppose 2 are present, then there will be 2 beta carbon. If 3 are present, then 3 beta carbon, and the hydrogen connected to that beta carbon is termed as beta hydrogen. Now if I talk about its mechanism, so it can happen in 3 ways, similar to this SN reaction, your substitution nucleophilic reaction, SN1, SN2 and SNI. It can also occur in 3 ways. The first one is E1 elimination, second one is E2 elimination, and third one is even CV elimination. So we'll look at it one by one, all of these types of your elimination reaction, and at last we will just compare that when it will give your substitution reaction and when it will give your nucleophilic reaction. So coming to the E1 elimination, so it is is a model which explain a particular type of chemical reaction. And here E1 stands for unimolecular elimination and has the following specification. Okay, so E1 means elimination that is unimolecular. Again, just invoke your previous concept. It was written SN1, which means that substitution nucleophilic unimolecular. That means the rate of substitution depends only on one substrate. Here also the rate of elimination will depend upon only one of the reactant, similar to that, because the rate will be now unimolecular type. Now if I consider the process of elimination in this kind of elimination, that is E1 elimination, then it occurs in 2 steps. First, ionization takes place, that is the H is removed independently, and then the deprotonation of the carbocation gives the alkene. So first, the halogen that is to be removed gets detached, and in the second step, your beta carbon is removed. Okay, and we get our alkene. Now, even elimination is better for your tertiary alkyl halide because it is possible with some and it is also possible with some secondary alkyl halide. So why is it written that way? Because if you see here, then what is being formed? This is, suppose this is your X. Now you have removed X, it will take your negative charge and this will be positive. Now again you are getting a carbocation, and you know what is the stability of carbocation, how it is affected by hyperconjugation and your inductive effect. So this one will form a stable carbocation, and hence even elimination will be more favored by this, like your tertiary carbocation. Secondary, it will depend on the conditions, but for tertiary it will be always your even elimination. Now, since it is a unimolecular reaction, so the reaction rate only depends upon the concentration of your alkyl halide. More is the concentration of alkyl halide, more is the rate of this even elimination, because the carbocation formation is the slowest step, because the first step I have shown you is the slowest step and it is the rate determining step. Therefore, first order kinetics is applied because it is unimolecular. Now, the reaction occurs in the complete absence of a base or presence of only a weak base. So it can happen at, say, your absence of base also. So if you are taking a strong base, then there is more chance that it would go E2 elimination rather than this one. Okay, so it is not dependent upon the strength of the base because it is unimolecular and it only depends upon your, say, this thing, that is your alkyl halide. Or in some condition you may be given a weak base. Weak base means like we can have this ETOH. Okay, weak base. Now this reaction gives thermodynamic products. This is very important. So I have mentioned earlier two types of products are possible. So the more substituted one is called as SATHEE-MED. Now this reaction only gives this SATHEE-MED product, that is more substituted alkene or more stable alkene. Okay, thermodynamically stable alkene. So suppose you have examples, two examples. Say first one is this hydrogen is extracted for in first case, and in second case suppose this is extracted, then this one will form the more stable carbocation, so it will give you even elimination faster. Okay, so remember, it is not totally one statement thing that you will say that which is more substituted will be reacting faster. So it will basically, you can say on basic level, it will depend upon the stability of your carbocation, and you know very well that this is delocalized. If it is formed, then it will be delocalized. And this resonance effect is much more pronounced than your hyperconjugation effect because it involves the complete movement of these pi bonds. And you know, sigma bonds are very strong to break, so their contribution is not that much efficient as compared to the pi bonds. Is this clear? Okay, now this thing is over. So we are done with this even elimination. Now we'll see an example of this even elimination. So I mentioned it earlier also, same thing is written, that even elimination in which the rate determining step is unimolecular, means the RDS is unimolecular, that is dependent upon one step only and does not involve the base. The leaving group in this step and the proton is removed in a separate second step that is being shown here. So if you take your tertiary butyl bromide, so this is a tertiary butyl bromide, 1, 2, 3 carbons are attached. Now what will happen? This Br will leave independently without any effect of this base. Now we have introduced a weak base, that is ETOH. It will take this or abstract this per proton and it will give you your alkene, that is isobutene. So is this clear to you? So you can see very clearly that this step, this reaction is occurring in two steps. First of all is the RD step, and that is the slowest step, and the second is your removal of proton. Now if I try to write the rate law, then it would be given as rate is equals to K multiplied by concentration of your substrate only, because it is a unimolecular reaction. So this is with the even elimination. Now what is this E2 elimination? So this E2 elimination is a single step reaction, unlike to this even elimination, which involves first protonation and then abstraction. It is a single step reaction with a single transition state. It is typically undergone by primary substituted alkyl halide. Okay, so primary substituted means this one. So since it will form the less stable carbocation until and unless that is a allylic halogen. So this should be kept in mind. So it is sometimes possible with the secondary alkyl halide and other compound. Again, this reaction is second order now, because since it is happening in single step, both the base and your concentration of your alkyl halide will decide the rate of reaction. So it is influenced both by the alkyl halide and base. Now it requires anti-periplanar structure. So this is the most important part of this E2 elimination. So in exams, you may be often asked to write the stereochemistry of a product, that whether it will give your E configuration or your Z configuration. So for that case, you must have a good understanding of this anti-periplanar structure. And to form the anti-periplanar structure, you must be good with your Newman projection, because it is very good in forming your anti-periplanar structure. So we will show you what is this anti-periplanar structure in the next slide. But for now, you must now have a good knowledge of this Newman projection or Sohaus projection, but I would say Newman is more efficient in this case. An anti-periplanar transition state has staggered configuration with lower energy than a syn periplanar structure, which is eclipse conformation. Now the reaction involves staggered configuration is more favorable by the E2 reaction. So what it is written, that an anti-periplanar transition state has staggered configuration with lower energy than syn periplanar, which is eclipse conformation with higher energy. So anti-periplanar is kind of, you can say it is a say this is the staggered configuration. So for things to get anti-periplanar, so we'll see what is anti-periplanar. It should have a staggered configuration which will have a lower energy. But if it is syn periplanar, then it will have a higher energy because there will be eclipsing. And the reaction mechanism involves staggered configuration, and it is more favorable for this E2 elimination. Now E2 elimination uses a stronger base. What does it use? It uses a stronger base. Why? Because I have told you just now that this E2 elimination is dependent both upon the concentration of your substrate and reagent. So our reagent is base, so it will depend upon the strength of base also. It will be strong enough to remove a weakly acidic hydrogen. So this are all the characteristics of your E2 elimination. Now we'll see the mechanism. So here is our mechanism. This is N-propyl bromide, normal bromide, and the bromine is added at the end position, and the reaction occurs in presence of ethanol. So we have taken ETO minus, it is a very strong base, and it gives propene. And the mechanism of E2 elimination is shown here. So since we have used the strong base, so it will go E2 elimination. Now what is this anti-periplanar structure? So you can see that this kind of configuration should be there. So if you look at this molecule in this fashion, from sidewise fashion, then you can see that they are parallel to each other, but their direction is opposite. So they are termed as anti-periplanar. So if there is only the chance of say your anti-periplanar, then only there will be formation of, or you can say the following of this E2 elimination. So here example of E2 elimination, there is anti-periplanar structure and H has been removed and Br has been also been released, and we got our alkene, which is propane in this case, and this is our transition state. So what's the difference here? You can see very clearly that it happens in a single step, kind of concerted mechanism which is similar to your SN2 mechanism. Now if you want to try the rate for it, then it would be given as rate is equals to K concentration of your alkyl, halide, and your base. So both of the concentration are involved in the rate law because it is happening in a single step. Now the tricky part with this E2 elimination is that it can go SATHEE-MED and Hoffman both. It can go SATHEE-MED and Hoffman both depending upon the nature of the reaction or the condition for the reactions. So let us see an example of how we can decide this SATHEE-MED and Hoffman. So this Hoffman, SATHEE-MED is the common one. Hoffman is for special cases. What is Hoffman for? It is for special cases. Now, what are the special cases? We'll see it. So talking about first of all SATHEE-MED. So if there is simple elimination, we have used a strong base. OET minus will extract this hydrogen. Okay. And we will get our, say, this thing in a single step. And plus we will get a Hoffman product as it is more stable. So according to SATHEE-MED, that alkene will be formed with more alkyl substituted and double bonded carbons. Now, the opposite thing is about Hoffman. How does Hoffman works? So for that you have to take this kind of substrate. Okay, for that you have to take this kind of substrate rather than this one. Now what will happen? Now the hydrogen will be eliminated preferentially from the beta carbon, which is attached with most number of hydrogen atoms. Therefore, according to Hoffman rule, the alkene will be predominant, which has less alkyl substituent. So it will take this hydrogen from less hindered side. So if you are taking such kind of substrate, then it will give your E2 elimination. Okay. Now, if you have a more hindered base, which is very hindered and it is not nucleophilic also, then in that case also it will give you E2 elimination. So this is a very good example of E2 elimination in which we are taking quaternary salt. So if you remember, if you react with your aliphatic amine with this diazotation, then you will end up getting this ammonium salt, quaternary ammonium salt, which on treatment with your NaOT in ETOH will give you majorly this Hoffman reaction. And this say our SATHEE-MED is also formed but in small amount. So this is the difference between SATHEE-MED and Hoffman. Now what is this E1CB reaction? So this is the third type of elimination reaction and you must have noticed it. So it is an elimination reaction that happens when a compound bearing a poor leaving group and an acidic hydrogen is treated with a base. So if you are having a weak leaving group, okay, weak leaving group or poor leaving group more appropriately, then the acidic hydrogen is treated with base. And E1CB stand here for elimination, one for unimolecular, conjugate base. And this reaction is unimolecular from the conjugate base of the starting compound, which is turned in form of protonation of this starting compound by suitable reagent base. So this is one of the example of E1CB, that is elimination, unimolecular conjugate base elimination. If you want a simple one, you must have noticed or not noticed, I don't know, but you have seen this kind of elimination earlier, or if you see it in the later class. Okay, you know that OH is a very bad leaving group. Okay, since OH is a very bad leaving group, it cannot go even, and in this reaction we do not use strong base also. Even though we use this strong base, and it would not have been helpful. So what happens here? So this goes like this, a conjugate base elimination. First this base will abstract this. Okay, this will abstract this, it will go here and will give you OH and this one. Now this negative charge will come back. This negative charge will come back and say this one will be removed. It will come here and it will be removed. So it can be written in this way. So we are taking here and here. Okay, clear? So this is clear. So in this phase, sorry, let me write it properly. So this kind of product is offered, and now this H is been taken. This negative charge once goes here, it comes back, and this OH is eliminated. This OH is eliminated. So is this clear? So if you remember, this is the case for your this aldol reaction in which even CV occurs. So first of all, this H is taken. Okay, this H is taken, and there's an electron withdrawing group. First it goes there, and then due to electron withdrawing group, this negative charge becomes stable. And after some time it breaks down, and your poor leaving group is even removed. Now the electron withdrawing group can be anything. It is generally carbonyl, aldehyde and ketone only, but it can be anything, any electron withdrawing group like CF3, okay, nitro group, electron deficient group, aromatic group. Dehydration of aldol is the most common even CV. So you must have seen this aldol reaction. Okay, so aldol reaction goes through this even CV only. So is this clear? Okay. Now this is the even CV elimination. So it goes like this. The base abstract this one. It goes here. And we get this kind of intermediate. It will come back. And now this OH will leave. This OH will leave. So is this clear? This is our double bond. It will come here and this OH will leave. Okay. Now let me draw it more nicely. So suppose this was your aldol product. Now you know very well that this OH is not a good leaving group. Now, but there is a hydrogen here. This base takes this hydrogen. It goes here and this kind of anion is formed. Okay, this kind of anion is formed. Now it will come here, this will go here and this will be removed. Okay, this is clear? Yes. This is the third type of elimination reaction. Now we will move to the next thing, that is the most important thing, that whether where do we take this substitution and where do we take this elimination reaction. For that we have to look at this flow chart. Now let us look at this substrate here. Suppose we are given with a substrate. First of all, look at the nucleophile or the base that you are given, the reagent. So if the thing is strong, then it will give biomolecular reaction for fix. Okay, so it will be biomolecular, because we know that the rate of reaction for biomolecular reaction depends upon the strength of this, say, your nucleophile also. For that reason only you are given a strong base or nucleophile. And if it is not so, then we will move to another form. Okay, so we'll see it later. Now first we will take in the case in which nucleophile is strong. So if it is strong and if it is bulky, if it is strong and if it is bulky, if yes, then it will give E2 elimination. And if it is not bulky, and suppose your substrate is 3 degree, it is not bulky but its substrate is 3 degree. So what cases do we take? First of all, if your nucleophile or base is strong, or your reagent is strong, then it will give biomolecular reaction. Now if it is bulky, it will give E2 elimination. If not, then it will depend upon substrate now. So now if your substrate is 3 degree, it will give E2. If it is 2 degree, it will give both SN2 and E2. Now suppose it is neither 3 degree nor 2 degree, it is 1 degree. Then in that case, it will give SN2 reaction. So is this clear? Okay. Now next, what happens if the nucleophile or base is not strong? Then we will see that which kind of substance it is given. If it is 1 degree, then it will give no reaction. So this should be kept in mind, that if your nucleophile or base is not strong, plus your alkyl halide is also 1 degree, then you will not get any reaction. But if your alkyl halide is 3 degree, 2 degree or 1 degree stabilized, then it will give unimolecular reaction. Now if the nucleophile is again bulky, then it will give E1. And if it is not bulky, it will give SN1. So this is a very good chart. You can solve some question using this chart and it will feel very good. I have used this chart too, and believe me, this is very helpful. Now last is the reaction with metals. Last one is the reaction with metals. So most of the organic chlorides, bromides and iodides, they react with certain metals to give compounds containing carbon metal bond. So here is a reaction of it. So it is very important reaction. You will see this reagent being used throughout the organic, that is called as Grignard reagent. Okay. So what do? We take alkyl halide, treat it with Mg, and then we see a bond has been formed or a metal insertion has been done here. So this Mg had been inserted between CH2 and Br. Now such compound are known as organometallic compound because it contains both carbon, which is for organic, and metal, which is for metallic, and then compound. So organometallic compound. So important class of this organic metallic compound is this Grignard reagent. Now, if I just move to next chapters, you will see that there is a very significant use of this Grignard reagent. Okay, so which is used for various purposes because it is a very good nucleophile now. Which is the nucleophile here? So since this Mg will contain your positive charge, this CH3, CH2 will contain your negative charge, and it is highly nucleophilic in nature. Okay, highly nucleophilic in nature. And if we react this with Mg in the presence of dry ether, we will get your Grignard reagent. Next, what do? We can perform another reaction in which we take our alkyl halide, treat it with sodium, then we will get your alkyl, or simply say alkane or hydrocarbon, I would say hydrocarbons, plus NaX. So Wood's reaction is nothing but your reaction with your reaction of alkyl halide with sodium, in which we get your alkane plus sodium halide. So this is a reaction with metal. You will see one more reaction in haloarene, which is termed as Wood's fitting reaction. But for now, if I try to summarize all your things, then we have seen this our elimination, substitution, elimination, and your reaction with metals. Okay, this is clear. So in substitution, one thing is being substituted by the other, in which we have seen SN1 reaction, SN2 reaction, and SNI reaction. Further, we have moved to elimination, which has three types again, which is E1 elimination, E2 elimination, and E1 CB elimination. Now this E1 is similar to your SN1 and E2 is similar to your SN2. Then we have seen a flow chart. Now that flow chart is very much comfortable with most of the reaction until and unless there is a play of solvent to role of solvent to play. So if there is a case of solvent, then things could get critical. But for now, you can take that thing for your final product. Okay, this is clear. Then we have seen this reaction with metals. Now, if you see the bond here, then this bond will get polarized. This will contain delta negative, and it will contain delta positive. And this delta negative will be very large because it is connected directly to a metal, and metal is very electropositive in nature. It will give its electron or donates its electron to CH3, CH2. If this is a Wood's reaction, you know what is the Wood's fitting? If your Rx that is being used are different, suppose we do not use 2 moles of the same Rx. Suppose we used an Rx and plus we used such kind of haloarene, suppose. And then we do this Wood's reaction. For that case, we'll see that we are getting a, say this thing. So this one will be termed as Wood's fitting. Now, if you want to know the mechanism, it goes like this. Suppose this is Rx. Okay. Now this is sodium metal. It has a free electron, so it will be donated here. Due to donation, both of the now electron pair will go on X and will form a X minus and R radical. Now another pair of sodium radical will donate here electron. which will give R minus. Okay, now we have this kind of reaction. This now R minus attacks here, and this X leaves, and we get our RR. And this X, two X's are being leaved here, so 2NX. So in this fashion, the reaction is occurred. Is this clear to all of you? So first of all, the Na donates this electron and X leaves with a negative charge on it. Again, since it is a radical and its octet is not complete, sodium again donates its electron, and there is a kind of negative charge on this R. Now this negative charge on this R, since it's very strong nucleophile, so it will quickly attack on this Rx and give your RR, and NaX will be kicked outside. So this is the mechanism for your Wood's reaction, and here is your formed alkane. Now let us look at this say our pathway once again, where we decided how did we decide this E1 elimination, E2 elimination, SN1 and SN2. So we'll look at it again. Again we will see this substitution versus elimination. So why I'm saying that substitution versus elimination? Because in some cases you will see you will face a dilemma that this is a kind of base also, because it is bearing a negative charge, it can abstract proton, and since it is bearing a negative charge, it can also act as a nucleophile and attack as a nucleophile. Now for that, two cases has been assumed. First, if the nucleophile or base has been strong, so if it is yes, then it will give biomolecular reaction. Next, now if your base is strong and bulky both, then it will give E2 elimination. If it is not bulky but the substrate is bulky, that is 3 degree or 2 degree, then it will give E2 elimination for 3 degree, and for 2 degree it will give SN2 plus E2. So strong will give biomolecular, bulky strong will give E2 elimination, bulky substrate in case of absence of this bulky reagent will give E2 elimination like 3 degree, and the 2 degree will give both SN2 and E2. Now if your substrate is 1 degree or methyl, then it will give simple SN2 reaction. So now if your base or your nucleophile is not strong and your substrate is also not bulky, that is 1 degree, then you will not get any reaction. Okay, suppose you do a reaction like this, which goes like this, that it is H3X E2OH. So this is a weak base plus this is a 1 degree alkyl halide, so it will not give any reaction. But in case if it is 2 degree or 3 degree or stabilized 1 degree, stabilized means suppose it is in this fashion. Okay, it is in this fashion like this, then the positive charge will be stabilized due to resonance. So if it is 2 degree, 3 degree or stabilized 1 degree, then it will give unimolecular reaction. Now which type of unimolecular? So if the nucleophile or the base is bulky, then it will give E1 elimination, and if it is not bulky, then it will give SN1 mechanism. Now under condition that favor unimolecular reaction, weak nucleophile base or polar protic solvent mixture of SN1 and E1 are usually obtained. So it is written here that under condition that favor a unimolecular reaction. So if we go up till here, okay, weak nucleophile and all of these are formed, then mixture of SN1 and E1 are usually obtained if you use polar protic solvent. So this is about the substitution versus elimination. This is very important for your product predicting, because it will give you a pathway, a proper pathway to decide a final product. So this was all for today's class. So we have seen all of the reactions, substitution, then elimination, and then reaction with metals. Tomorrow we will move to our haloarenes and see what is the acidity and basicity of this haloarene reaction, preparation, all of this we will see tomorrow in the next lecture. Okay, so we are done with this haloalkane and we are left with this haloarene. So thank you for your time. With this I would end my lecture.